to D converters. Now, because there are not a lot of people that are interested in A to Ds, I'm going to go through this kind of fast because this is just some of the components we have. But I think you'll be duly impressed by our technology. First of all, the ADC 1175 is an industry standard device. 5 volts, 20 megasample per second, 8-bit A to D converter. One of the nice things about it is we have absolutely the lowest power consumption on the market. 55 milliwatts typical, 85 maximum. Everybody's device comes in a 24-pin SOIC EIAJ from Japan. That's simply because of the fact that the first 1175 was the Sony CXD 1175, back, would you believe, somewhere around 1969. Okay? It was expensive back then, but the technology has improved and we've got the price lower. It also comes in a 50 megasample per second version. Now, what is ENOB? ENOB is effective number of bits. We take the combination of SNR and THD, we end up with what? Synad, right? You take Synad and you say, okay, the theoretically best Synad for a given device, let's say an 8-bit device, is about 50 dB, 49.9 dB. That's the best Synad performance you can get. That is, if the only noise is quantization noise, because of the fact you have a digital output and they're discrete steps, so there's some noise that's there, and you have no distortion, none whatsoever. You end up with 49.9 dB is your Synad, signal to noise and distortion. And of course, the signal to noise is the same. Your THD is minus infinity. There is no distortion. The ideal component. So, if we say, okay, we take whatever Synad we have, and let's relate that to an effective number of bits. That says this converter operates as the ideally perfect converter that has 7.2 bits of resolution. Now, you're not going to get a fractional bit, but that's the equivalent. Components are there. Okay. Performance. This is the performance of the leading 3 1175s on the market. Most of them are kind of old. They've been out there for a while. One of them is new and was introduced after ours, as a matter of fact, but they use the basic technology of Sony, as a lot of people are doing. So what we've done, we've come up with a new topology, a new architecture, a new way of doing the A to D converters that rely on, would you believe, very small capacitors, down around 15 femtofarads. It's very small, so they discharge quickly. So we can't operate our device lower than 1 megasample per second because you start losing charge on the capacitors. However, I think that you'd be surprised when you see, compared to the other most popular devices, we have a Synad performance that is like this. It's flat. It's flat. This is the reason that people that are using this part are switching to National Solution. And we do this, that I could show you, and in your CD-ROM there are other devices, plots of what we do with other devices that are similar to this. But I'm just showing you this one as an example. Okay, 1173 is a 3-volt version of that same component. This is a mistake. It's, oh, sorry, it was not. 1173 is correct. 7.5. We corrected it. 7.5 effective bits. This is a 15 megasample per second part, 3 volts, or 3.3 volts. And it's available in TSSOP, very small package, industry standard pinout. And look at that power, 40 milliwatts. We're getting way down. Okay. Front end using 1173. What we have here is everything we talked about before. Padding the input and then adding gain, this RC, clock considerations, but we have one new thing here. Why do we have those resistors? I suggest you need that whenever you have any kind of digital output from a mixed signal component. The reason is this. You have bus capacitance out there, whether that bus is a single component or whatever. You have some capacitance out there. As you try to charge and discharge that capacitance, you're supplying current from your supply, causing your supply. You'll see the 409 we have, we talked about those before. Very low value components because that's typically what's recommended by the 409. Now, The spec calls for something around 150 ohms here. We find that when you're driving an A to D converter with its switching capacitor, it likes to have a little bit lower feedback resistor. My message here is, although you have generalized rules on a data sheet, don't be afraid to experiment. You may find something that's better. You may find something that's better. Everything else here is strictly what we've talked about except for this beat. What we have is we have separate pins to drive the output lines, the digital outputs. And the reason for that is maybe you want to only put 3 volts there. The rest of the circuitry is 5 volts. Maybe you want 3 volts because you want to drive 3-volt logic. Okay, you could do that. But we should have that decoupled from everything else because it's a fair amount of power there and you don't want the bouncing of that line to affect. Okay, that has allowed for a lot of the electronics to be combined. We've taken our 9830 and we've done this. Everything but the memory, the power, and the power transistors, and of course the power supply, one chip. This is the reason why prices of scanners have come down. We're the only one with this complete solution. Not only that, but we've got to take a document that has been scanned and then re-scan it. What you find out is you get something like this. You have an interference pattern. The reason is, when you look at this, if you're trying to go from 600 to 150 dpi, dots per inch, for example, you take this 4x4 block and you say, I'm going to look at that first pixel and I'm going to assume that whole thing is going to be what that one is, dark in this example. Look at the first one here. Most of it may be dark, but you're going to assume it's white. So you end up with an interference pattern. We have gone and we say, we're going to look at all 16 of those things and we're going to average that. And we end up with this kind of performance. Now you only went too far, didn't you? You end up with this performance. The only time you're going to get this interference pattern if you scan a document that has already been scanned. A scan of a scan, if you will. Otherwise you won't see this. Okay? Now I'm going to go beyond this because I don't want to bore you. Okay, temperature sensing.